Hi, all right, we're here for taking a look at AP Physics and looking at using Coulomb's law, modified form of Coulomb's law to find the field from an extended region of charge. What I want to do is look at this problem, problem 5 actually on homework set 2, that says a uniformly charged insulating rod of length 14 centimeters is bent into a semicircle. And the total charge on the rod is negative 75 microcoulombs. Find the magnitude and direction of the E field at 0, the center of the semicircle. So that one looks like this. We draw a sketch. We have an insulating rod, and we bend it into a semicircle. Okay, and we're trying to find the E field strength there at what would be the center of the ring if it was bent into a whole ring. So right there, we're like, hey, how big is the E field? Okay, now they told us the total charge on the ring, or semicircle I should say, the rod before it was bent, is negative 75 microcoulombs. Okay, so this is negatively charged, negative, all the way around. And so right away, you can say, hey, if I was here, what direction would the E field be? And you're going to say, well, that electric field, it always shows which way the force is on a positive. You say, if I had a positive charge here, it would be attracted to all that negative. You say, well, there's equal amounts of positive lower by symmetry here. You say, being attracted up and down. You see, those vertical parts are going to tend to balance. It's going to get attracted straight left. So I know my answer is going to be an E field going straight left. Okay, now let's start talking about how we calculate this. They tell me the length of the rod. They also tell us the length of this thing is 14 centimeters. So that's 0.14 meters. I think that's like all the given information, right? Yeah. So I should just comment, obviously we know that micro means times 10 to the negative 6. So this is negative 35 times 10 to the negative 6 coulombs. I know, I just wrote too small for it to be picked up by the camera well. Sorry about that. But anyway, here we go. We're trying to find the E field there. So you say to yourself, well, what we're going to do is, I realize using a modified form of Coulomb's law, we're going to take this charge and we're going to split it up into a bunch of little bits of charge and then add up the E fields from all the little bits here. Okay, so that setup looks like this. Again, we know that Coulomb's law is that the electric force is K, Q over R squared, right? Q and Q over squared. But I'm trying to find the electric field strength. And remember that E field strength is the electric force per charge. So if I take this FE and I divide out by one of the charges, right? I'm trying to find the field strength here. It's as if I had a little charge here. I want to know like what the force would be per coulomb that I put there. So I take my electric force per coulomb that I put there. So like the Q2 here, basically, we're going to kind of cancel out there. So my E field ends up looking like, I don't know why I just erased that. It's my FE per Q. My E is going to be KQ over R squared. This is the E field, a distance R away from a point charge Q. So what I'm going to do though is I'm going to split this up in a bunch of little DQs so I can find the total field. So if I looked at just one little bit of charge, so I go slice, infinite number of infinitesimally small little DQs. And I just talk about like one of them. Like say like, I don't know, this little bit of charge here. That little guy. You say right there, that is a little DQ. You say that guy would make a little bit of E field here. You say that electric field, since this is negatively charged, the field would be towards it, a positive charge would get pushed towards it. So I would have a bit of field here. Now this is an infinitesimally small little bit of Q. So it's going to make an infinitesimally small little bit of E. Little DE there. I'm trying to find the total field. I want to add up DEs from all the little DQs going around. So you get the total E, right? I would just integrate, yeah. So I'm going to get that E is the sum of the K dQ over R squareds. But there's a catch. The catch is that E fields are vectors. They're arrows. And when you go to add arrows, I'm going to be adding up arrows, little E field arrows all the way around for all these DQs. Well, every little bit of charge up here, there'd be symmetrically a little bit of charge down below, right? Kind of a corresponding little guy here. This little DQ. This little guy who's opposite him, he'll make an E field going towards that negative charge. And this DE and this DE, when I go to add them up, I have to add them like vectors in. I got to break into components and add them up. If we did that, check it out. This top guy would be to the left and up. This guy would be to the left and down. The symmetry here, this part up and part down, those would tend to cancel out. Tugging upward, tugging downward. The horizontal bits would add though. I really don't want to add up all the DEs mathematically here. I want to add up just the X components. These horizontal components along the X-axis. So what I really want to do, if I call this angle theta, is I want to add up this horizontal bit, hypotenuse times, this is the adjacent, so I'm going to do hypotenuse times the cosine of theta gives me the adjacent. I want the X component. So I want to just add up all the X components of DE, right? And that would be E cosine theta. Then I want to add up all the DE cosine thetas, really is what I want. Does that kind of make sense? So yeah, but let's just write that up and say this is going to be E in the X. It'll be the X, the E field in the X, which will be the total E field because the vertical parts cancel. I just have to have a cosine theta thrown in here too, into that interval. All right, so that's the idea. My total E is just the E in the X. The E in the Y-axis cancels out. Okay, that's an important thing to realize. If we don't realize that, and we start adding up all these total E arrows, if I start just adding the lengths of all these, I'm going to get an answer that's too big. I'll be ignoring the fact that the vertical parts cancel, and my answer won't be right. It'll be way too large. So that's the idea. Now, when I go to take a look at this interval, I've got an issue. Here I am going around, going around, going around, going around. As I go along, adding up my little DQs times this chunk, you say, well, K, that's a constant, so we could push that out of the integral. R, the distance between the little bits of charge and the point where we're measuring field, hey, that's a constant. That's nice because it's a semicircle. But the theta is going to be changing. The angle is going to be changing as we go. And, of course, the little q is changing. So I actually have two different variables here. And so you know we have two variables. We need to rewrite one of them in terms of the other or both of them in terms of some new third variable. So it's just one variable so that I can take the integral. So how are we going to do this? Well, we're going to use something from the rotation unit, actually. Actually, we introduced this idea way back in the energy unit, this little substitution. It's going to be a relationship between, well, here we go. I'm going to end up, I'm not going to do this integral in terms of Q. I'm going to end up turning it into something in terms of theta. So you're like, okay, I got to get charge in terms of angle. And you're like, that seems awkward. I'm better, since we've done before with rods, is we talked about like charge per length. So we're going to start with that. So we'll talk about what we would call this. We would call this our linear charge density. How densely packed the charge is, you know, per unit of length. And so that guy will use the variable lambda, and that will be my charge per length, right? So because it's uniform, if I had half the length, I'd have half the charge, a third of the length, a third of the charge. D length would be a dq. See where I'm going with this? A little d length. So rearranging this dq, the thing I need to rewrite, could be written as lambda d length. Now, a little bit of length here. You say, well, each one of these little dq's, that's like a little d length along this guy. Then we want something in terms of angle here. And then you say, wait a minute. We did look at a relationship between if something's going around changing angle, like rotating. We talk about the angle, and we talk about the linear quantities going around here. There's a relationship between how far you go around in an arc and the angle change, right? Usually we call the arc length S. Usually use S for arc length. dl here along length, that is also ds, right, the arc length. Once I write it like that, hopefully some things start to click. The arc length. And you say, is there a relationship between arc length and angle? And you say, yeah, arc length is r theta. Remember that? Okay. How to relate my angular displacement with my linear displacement along the arc. So what I'm going to do is I'm going to take, what I want though is this dl, that's an arc length, that's like ds, right? Okay, fair to say that. The length along the curve, along the arc is ds. Okay, I need a ds to replace. So I'm going to take the differential of both sides. So I'm going to say, hey, what's ds going to be? Well, if you want to take a derivative of two variables multiplied by each other, you like have to do the product rule, right? It says I want to go ahead and do r times d theta plus theta times dr, right? The thing is, so I take the radius times a little change in angle, and then the angle times a little change in radius. See, but wait a minute. As we go around here, this thin rod, as we go around adding charge, are we changing that radius of the circle? You say, no, it's a constant. The change in r is 0. R is a constant. And so this term drops out. And so ds is r d theta. Hooray! And so I can replace ds, the arc length, which is here, with this guy. So I'm going to get then that dq, right, is lambda ds. That'll be lambda. ds will be r d theta. And so I'm going to replace dq in the equation with lambda r d theta. Be like, it's like I did like a double substitution here. Weird, huh? Yeah. Anyway, lambda r d theta is going to take the place of q, and now I'm going to have an expression with only one variable, theta. So my E field now is going to be my integral k. I'm going to go ahead and push that cosine theta there. Okay, dq is going to become lambda r d theta. So here, my denominator here was r squared. There we go. Okay. Something I need to fix is I didn't even bother writing the bounds on this original integral, but it would have been adding up all little bits of charge until I had the full charge on the rod added up. It would have been like from 0 to big Q, right? The full charge added up, adding up the E field made by all the little bits of charge all the way around. Well, now we're going to do it in terms of theta. So you're like, well, what angle should we call this? I think that when I did this before, I went ahead and I defined my angles like from like the reference angle on the right here. And so my theta here actually would have been this. But you know, the cosine of this angle, this big angle theta, is the same as the cosine of this little angle here, right? You know what I mean? Just the sign flips or whatever. But anyway, I guess this theta here then, I'm going to do it from, as I go from this angle. Now I'm going to do this at first from here to here. So that angle here would be, do you want to use radians? Well, I guess we're supposed to use radians when we use this, aren't we? So you say, yeah, this is going to be from pi over 2 to like point down. So it's going to be swinging from here, sweeping through there, from pi over 2 to 3 pi over 2. So from theta is pi over 2 to theta is 3 pi over 2. Those are my bounds. All right. All right. So I've now, at this point, I've turned it from my original setup into a problem with an integral I can actually solve. Let's take the constants out. Sound good? K is a constant. Oh wait, you see there's an R there and an R squared there? So, bam, bam, that's nice. So I've got K, lambda over R. Those are all three constants that can come out. I'm running out of room to show my work. Am I going to try to squeeze it in here? I know you're thinking I'm gonna, aren't you? You're thinking I'm gonna, aren't you? Yeah, I am. Squeeze it in here. So when I do this, my E is going to be K lambda over R. Yeah. And now I've got the integral of cosine theta d theta from pi over 2 to 3 pi over 2. Okay. Hey, what's the integral of cosine theta d theta? Hey, what will give me cosine as a derivative? Well, the derivative of sine is cosine. So this is going to be sine theta. Evaluated from pi over 2 to 3 pi over 2. Right? That's what that integral comes out to be. I still have this K lambda R. At this point, I'm going to try to do a couple things at once. Hey, over here, K, that's all right. That's a universal constant. That's, 9 times 10 to the 9. We're fine with that. Lambda wasn't given. That's a variable we made up. So that was our charge per length. They did tell us Q and they did tell us L. So I'm going to get my answer in terms of Q and L. So I'm just going to substitute Q over L back in there. KQ over L. Now wait, what about this R? They tell us the radius of the circle here? No, but we do know that if you do half a circle, that's 14 centimeters. So you're like, all right, can I figure out what that radius is, that radius of the circle? You're going to say, well, I know that the whole way around a circle would be 2 pi r, right? And so, but 14 centimeters is half the circle. L is half the circle. So L is half of 2 pi r. Rearranging, you say cancel the 2's. L is pi r. R is L over pi. Okay, so it says R there, I can put L over pi. L over pi, let's keep the pi up on top, and L squared there. Okay, so that's it. So I just used, I did a bunch of algebra at once. Sorry about that. Lambda is Q per L, and R is pi, L over pi. So I did both those substitutions, and I got this. Okay, hey, I'm just going to do final minus initial. If I did that, you would say, hey, this chunk here, sine of 3 pi over 2, I'm just going to do this real small. Sine of 3 pi over 2 minus sine of pi over 2. And you say, hey, wait a minute, the sine of 3 pi over 2, that's going to be, sine is the one that starts at 0. When it gets up to 90 degrees to pi over 2, that's when it's at maximum. That's when it's 1. So this is actually, and when it gets down to here, that's negative 1. This is negative 1 minus positive 1. And see, if you do that negative 1 minus 1, that's negative 2. So this chunk just comes out to be negative 2. Put it in here. So I'm getting this negative 2. It's common to put the numbers out in front, right? 2 and then constants. So that's my answer there, right? That negative sign, you're like, when I do Coulomb's law, I'm generally just getting the absolute value, right, of the charge is what I'm putting in there. Direction is something I put on myself. It is true that it is in the negative direction, though, so it's kind of handy. Maybe I'm okay with that. My E is here, this negative 2 pi KQ over L squared. All right, and I'm indicating negatives to the left. Then that's it. Hey, now I do have values here. I can put the numbers in. 9 times 10 to the 9, 75 times 10 to the negative 6, and my L of 0.14, and get my answer for field strength. Like I said, I really ought to just absolute value this stuff and get a positive answer for the strength, and then just say that it's to the left, towards the circle of the rod. Put our numbers in. Yeah, sure, why not? This is what it looks like variable-wise. If I just throw the numbers in, man. Wish I had more board space. So then my E field strength would be 2 pi 9 times 10 to the 9. My Q is 75 times 10 to the negative 6. I'm just taking absolute values here. And then over that length, 0.14 squared. Okay. And if I punch that in my calculator, two times okay, and so I get a ridiculously strong electric field, actually, out of this. I got this value that was, that makes me nervous when I get a value this big, but we're going to go with it. I got like 2.16, I'm rounding here, times 10 to the huge amount. 1, 2, 3, 4, 5, 6, 7, 8. In the 8. And my units for E field strength, remember E field is the force per charge, so it would be in newtons per coulomb is the unit for electric field strength. There we go. Right? And it's directed to the left, okay, in the picture. All right. And that's that problem. So to sum up, what's the stuff I want you to think about with this one that I want to introduce here? Again, the idea that when I go and I add these components, recognize that of E field as I go around, that parts are going to cancel. That E is a vector. It's an arrow and it's got to add like arrows add. And so we really just want to add horizontal components. The idea that if I'm going around in a ring like this, adding up charge, it makes sense to do it in terms of theta, from this angle to this angle sort of thing, as I'm adding up the little bits. And remind you about this handy substitution, where I can talk about the differential form and see that that little arc length is r d theta, okay, and do that substitution. That's it. All right. Thought I'd share that one with you.